All right, welcome. Today, we're going to pull back the curtain and look at this secret language of materials. We're going to figure out the basic rules that decide why everything around us, from massive bridges to tiny paper clips, either holds together or, falls apart.
And it all really kicks off with a pretty simple question that gets right to the heart of material science. Have you ever actually stopped to think about why you can bend a paperclip into some new, weird shape, but if you try to do the same thing with, say, a glass rod, it just snaps in two? The answer is all about how they react when you push or pull on them. So to get to the bottom of this, here's our game plan. First, we'll break down what stress and strain even are. Then we'll look at their relationship on something called the stress-strain curve. We'll compare ductile versus brittle materials, get into a little detail about engineering versus true stress, and then wrap it all up with why any of this actually matters in the real world. Okay, let's get into it. To understand how any material behaves, you have to meet the two main characters in this story, stress and strain. First up, we've got stress. Now imagine you're in a tug of war. Stress isn't the force you're pulling with. Nope, it's the force inside the rope, spread all across it, fighting back against your pull. It's that internal resistance, and we measure it in things like pascals or psi. And all that internal stress, it causes something to happen. That something is called strain. Strain is just how much the material actually deforms or stretches. So if that rope in our tug-of-war was 10 feet long and it stretched by 1 foot, the strain is 1/10, or 10%. It's just a ratio, so it doesn't have any units.
So here's the absolute bottom line, the most important thing to remember. Stress is the cause, and strain is the effect. You pull on something, that creates internal stress, and that stress results in physical strain. You literally can't have one without the other. They are the fundamental power couple of material science.
Okay, now what happens if we plot this cause and effect relationship on a graph? Well, you get something incredibly powerful, the stress-strain curve. And you should really think of it as a material's autobiography. It tells you its entire life story under pressure, from the first little tug all the way to its final snap.
You know, the process is pretty straightforward. Engineers take a little piece of a material, they stick it in a machine that just pulls on it, and they measure exactly how much stress is building up and how much strain is happening. The graph they get from that reveals everything: its strength, its stiffness, its whole personality.
So the story always starts in the same place, the elastic region. On the graph, this is just a straight line. Here, stress and strain are perfectly proportional. That's a famous idea called Hooke's law. If you let go of the material, it bounces right back to its original shape, just like a rubber band. And the steepness of that line, that's its Young's modulus, which is just a fancy way of saying how stiff it is.
But if you keep pulling, you hit a supercritical moment, the yield points. This is the point of no return. Once you go past this point, any deformation is permanent. The material is now in what we call the plastic region. And this is exactly what's happening when you bend a paperclip. It stays bent because you've pushed that steel right past its yield strength.
Now this is where things get really interesting. As you keep stretching the material in this permanent plastic region, something kind of weird happens. It actually gets stronger. It's a process called strain hardening. Basically, the atoms inside are rearranging themselves, making it harder to pull them apart even more. This goes on and on until the material hits its absolute peak strength, a point on the graph we call the ultimate tensile strength, or UTS.
After hitting that peak, well, the end is near. The material can't take the stress evenly anymore, so one little area starts to get thin and shrink down. We call this necking. Now all the force is focused on this one tiny weak spot, and from there, it's a very fast trip to total failure or fracture.
What's so cool is that the unique shape of this curve, how it goes up, if it plateaus, how it ends, it basically tells you the material's whole personality. And we can generally group these personalities into two main types, ductile and brittle.
On one hand, you have ductile materials like steel and aluminum. These are the stretchers. Their stress-strain curve shows a long, drawn-out plastic region. They deform a lot before they finally break. On the other hand, you've got brittle materials like glass or a ceramic plate. These are the snappers. Their curve has almost no plastic deformation. They stretch a little bit, and then bam, with almost no warning, they just fracture. And this table here really brings it all together. And it takes us right back to our very first question. Why does a paperclip bend? Because steel is ductile. It can handle a huge amount of plastic deformation, and it necks down before it breaks. And why does the glass rod snap? Because glass is brittle. It fails suddenly with barely any deformation, and it just can't absorb a lot of energy before it gives up.
Okay, so now it's time for a little pro-level insight. The typical stress-strain curve we've been looking at, what we call the engineering curve, well, it doesn't actually tell the whole story of what's happening inside the material.
I mean, just think about it for a second. As we're pulling on that piece of metal and it starts to neck down, what is actually happening to its cross-sectional area? It's getting smaller, right? The standard engineering curve completely ignores that fact.
And that's the whole difference. Engineering stress is calculated using the original area of the sample, from before the test even started. That's why the curve seems to drop after it hits its peak. But true stress is calculated using the actual instantaneous area as it's shrinking. And when you do that, you see that the stress inside the material is actually going up, 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 all the way until the moment it breaks. It's a much more accurate picture of what's really going on.
So, why do we obsess over this curve? Is it just for fun? Absolutely not. Understanding this relationship isn't just some academic exercise. It is the fundamental language that engineers use to build our entire world safely.
Seriously, every single time you cross a bridge or you fly in an airplane, you are putting your trust in an engineer's understanding of this curve. It's why a skyscraper can sway in the wind, why landing gear can absorb the impact of a 400-ton jet. It's all about picking the right material for the job, like using ductile steel for a car's safety frame, because you want it to crumple and absorb energy in a crash, not shatter into a million pieces like glass.
And to make sure nothing ever goes wrong, engineers never design things to work at their absolute maximum limit. They always build in something called a factor of safety. So if a part has a factor of safety of 1.5, it means it's built to handle 1.5 times the biggest load anyone ever expects it to see. It's a critical safety buffer, and it's based directly on the limits we see in that stress-strain curve.
At the end of the day, that's what this is all about. This one simple graph is a universal language. It translates all those complex, invisible forces happening inside a material into a clear, visual story that lets us build things that are both reliable and incredibly safe.
So the next time you see a massive skyscraper or a sleek jet, just remember that its very existence is thanks to this simple line on a graph. The stress-strain curve isn't just a bunch of data, it's literally the blueprint for innovation. It's what allows us to keep pushing the boundaries, building the future, one material at a time.